So this is the tree in T7 2, because there are 2 roots and there are 7 non-rooted vertices. So from this, of course, we need to map back to the Poynting function. So if we already have this tree, this forest, so when we write the forest, for each line, for each generation with the same parent, we always write the small one to the left side. So we can index all of this from top to bottom, from left to right. So first one, the first level, so it's 1, and then 2, and then the second generation, 3, 4, 5, 6, 7, 8, 9. So the map is very easy. We just map this to its parent index. So 3 will be mapped to 5, because 5 is 3's parent index. 4 will be mapped to 8. So you can check this is correct. So we map it back to the two-part function. So in enumerative combinatorics, the class of integers usually have some natural statistics. So for example, for a finite set A, the cardinality equals to the summation of 1 for each element. So this is counting. And we can also weight the counting. Here, the F is the statistic we care about. And usually we study on the sequence of finite sets. So if we have a sequence, we can have a sequence of its size and the sequence of polynomials. And sometimes the statistic F defined on the sequence of sets have some limiting distribution. So if we let in F be its expectation, and var n of F be its variance, then we can also think about this random variable. It's a skewed random variable. So now let's talk about these two statistic. So the first one is the sum. It's just we add up all elements in the Polynomial function. And the second one is called area. It's very similar with the size. So now we have this weighted counting polynomial. I use here use PNA to denote the set of a parting function of that set. So of course there are connection between them. And we have similar recurrence relation for P and Q. Especially for P, it's very similar with P and A. So the only difference is here we have x to the n, and for P and A there's no system because when we consider the number of ones and when we delete them, and then for each remaining term minus 1, it means after one operation, the sum of the Polynomial function will be n less than the original one. So here we need to add x to the n. So now we have considered the expectation of the sum for a parting function of less n. So for the numerator, we take the derivative for the polynomial Pnx, then let x to be 1. So the denominator is just the number of a parting functions of less n. And there is a formula for this, so it will be in terms of a and n.
Doesn't matter some formula. Doesn't matter the exact form of the formula. Not relevant.
Oh, you mean I don't need to write this?
That's why some formula.
Oh, okay. Let me just finish this part.
Correct. this formula is due to two people I don't like.
Yeah. So for the area, there's a similar one, but we can also write the area like this. So what is Wn plus 1? There's a definition for Wn. So this is proved by Riordan and Sloan to be the expectation of the height among all rooted labeled trees on vertices. So there's a sequence of it's asymptotic to n to the 3 halves, and then there's a sequence in OEIS, it's A435.
And it's a very important sequence. It's the first sequence in OIS. And this has OIS started.
Yeah, so because it's not A1, because at first they ranked it by the initial
lexicographic order.
Yeah.
Initially, in this long order, they did in lexicographic order the first batch. So that's why it's not A1, it's certainly A1.
And for the limiting distribution, so for this random variable, there is a limiting distribution is it's called how to pronounce it, array distribution. So it's proved by many people. You can just Google it and you'll find it. So now let me choose an exact formula for the factorial moment. So there's a fact for this E1NA, it means for area. This is expectation. So for all higher moments, actually they are for higher moments, EKNA, it can be written as a polynomial of NA plus another polynomial of NA times E1NA. So in the case of the most interesting one, when A is 1, in this case E1 is asymptotic to n to the 3 halves. So for the second factorial moment, there's a formula. It equals to a polynomial times E1 of n and plus another polynomial. So for the third factorial moment, it's similar. But the formula is much more complex, so to save time, I won't write it. So WC and I calculate all the factorials up to 30.
bigger computer, you can easily get up to 100.
Yeah, sure. If you use a supercomputer in a basement. Yeah. So we will have the ek of n is asymptotic to some coefficient times n 3k over 2. Where ek is a sequence of moments of array distribution. This formula is quite complex. It's something like but for RK, that's also a very complex formula.
So it's recurrence.
Yes, it's defined by recurrence. So, because we compute up to 30, so at least for k from 1 to 30, we almost prove it is an array distribution, and with only elementary and finitistic method. And this is a joint work of Dr. Z and I, and it's also on archive, and it's already accepted. So
It's going to be accepted in the famous journal with Medical Intelligence. Thank you very much.
many thanks to Dr. Z, and thank you for coming.
Thank you very much. Yukun.